So let's get started with feature selection methods by looking at an overview of different feature selection methods. Feature selection is also called dimensionality reduction, and for that reason it contributes to data reduction. It's very important in biomedical data because there are a large number of features available. This is referred to as a curse of dimensionality. For example, the number of gene expressions. Even though the data are going to be recorded on, for example, DNA microarray, it has some values associated to most of the genes available in the genome. So we deal with a large number of features. Features also are called attributes or variables. They are the constants in the data set we have been talking about. And we have one value for each feature for each row. And often in studies, because there are so many features, you may have tens of thousands of features, sometimes more, it happens often that the number of rows is smaller, and that's then a challenge to address, and that's called the curse of dimensionality. There are many feature selection methods available. So this is an example that illustrates why it's important to do feature selection and how feature selection, again, it can be considered as a data preprocessing step, because the goal will be, for example, here to classify a duckling or a little bird, to know whether it's a little duck or whether it's a little swan or another kind of animal. So the question is, what features are important to detect really what kind of duckling this is, and so that we can very quickly and easily identify what type of duckling this is. So it's a pre-processing for the data analysis. Now let's look at an overview of feature selection methods. So what kind of challenges are in the features? They may be redundant. Sometimes there are duplicate features. The information is already contained in other features. For example, age and date of birth represent the same information, so they can be considered as duplicate in some cases, not always. Another challenge is that features may be irrelevant. They do not bring valuable information for the data analytics task. For example, very often datasets are going to have some kind of identifier. For example, a patient ID for a patient record. The patient ID will not be relevant for the analysis. When we aggregate the data together, the patient ID will not be relevant, so we don't want to consider it for data analysis. Features may impede the data analysis method from performing well, and that's an issue called overfitting. I will talk many times about this topic during this course because this is a main drawback to avoid. We don't want to build models that fit perfectly the data so that they cannot be generalized. We want models that can apply to new data that we don't have yet, and not models that can apply only to the data that we have. When the models work very well on the data we have but don't generalize well, this is called overfitting. And when you have too many features, that's really the danger, is that you're going to build models that fit perfectly all these features, but then on new data, they will not fit at all. So that's why determining which features are important for the task at hand is going to be so essential to get good data models. Now the question is, you may ask me, why don't we just consider all the subsets of features when we want to select and then choose the one that works the best when we test our data model? The issue with this approach is that it's often not feasible, particularly when we deal with a lot of features. Feature selection can be illustrated like here as a search in a space of subsets. We have 3 features here, and we can select subsets that have no features. 1 feature, we have 3. 2 features, we have 3 also illustrated here. But of course, 3 features to start with is not big. There is a formula that gives a number of subsets of features for n features. For n features, you have 2 power n subsets possible. 2 power n, because n is an exponent, it's going to be what's called an exponential problem. These types of problems are known for requiring a lot of computing power. So, and you know, in many cases, when n is too large, we won't be able to calculate all the possible subset of features. For example, if n is 20, 20 is not such a large number of features, you would have 2 power 20 possible subset, which is over 1 million. So you're already in a non-tractable situation. So imagine when you have tens of thousands of features, you cannot consider all the subset of features. So you need to apply what's called some heuristics to select the best subset of features. So feature selection aims at automatically finding a minimal set of relevant features for future tasks such as diagnosis, treatment, etc. So again, it's part of the pre-processing of the data. For example, very often we want to select genes that are particularly associated with some diseases. You probably know about that. There are some genes that have been identified that are associated, for example, with breast cancer and with other diseases. But this is general about many, many diseases. So here, for example, we have 4 genes. We have gene 1, 2, 3, and 4. We have 2 individuals, E1 and E2, or 2 cases of normal subjects, and 2 cases of tumor, E3 and E4. And then you want a test sample, and you want to know, based on these features, how do I know whether this test sample is a normal or a tumor? We see that if we select gene 2, we're not going to get any information because gene 2 has the same type of expression both in normal and in tumor. So you definitely want to look at gene 1 and gene 3. And so based on the values of gene 1 and 3, I would say this test sample is normal. So you see how we can select. Here is a good example of how we can select some genes by comparing how these genes are expressed in normal and in tumor. And when these expressions are different between normal and tumor, then to characterize a tumor, we're going to select these particular differentially expressed genes. Very often, feature selection methods operate 1 variable at a time. We can see here. So it's going to be 1 variable at a time. To do that, we have a lot of methods available. You can calculate a t-test. It's a statistical method between the 2 classes, for example, 1 class being normal, the other being 1 type of tumor. You can also calculate a correlation coefficient to see how correlated the feature is with the diagnostic class. These are numeric methods, statistical methods. There is another one that I will go into more detail about, which is called the between group to within group sum of squares, BSS, WSS. So these are some examples of feature selection methods that consider 1 feature at a time. And then there is multivariate gene selection methods that consider multiple genes simultaneously to exploit the interdependence between genes. Again, the goal is still the same, to reduce the number of relevant genes. Sometimes, as you see in this example, you have two genes and several classes, class 0, two classes, 0 and 1, and some cases. And you see that the class 1, for example, could be a tumor type of class. You see that it doesn't have these two genes, 1 and 2, overexpressed. Overexpressed is a red. Whereas together, it's pretty much an OR between the two. So here, if you have an OR, only one of the genes 1 and 2 that is overexpressed, you are in class 1. While if both are overexpressed or underexpressed, you are in class 0. So that's called, to do this kind of gene selection, you need to do multivariate gene selection. More generally, feature selection methods belong to several families. Filter methods, where features are selected independently from the data analysis task. Wrapper methods, where features are selected based on their performance in the data analysis task. And the last one is embedded methods, where the feature selection is performed during the data analysis task. In that case, this is not really a preprocessing task or part of the preprocessing task. So here, for example, the filter method would select features independently from the task of determining whether a duckling is a little duck or not. And the wrapper method will select features that improve the prediction of whether the duckling is a little duck or not. Some methods map the present features to another space where they may become more meaningful. This is a case of such method we're going to see in the future, like supervector machines, in signal processing methods as well, like a Fourier transformation or wavelet transformation, and statistical methods such as factor analysis or principal component analysis. We see here an example of a Fourier transformation. We see that we start with a lot of data, and we're going to map the data which is temporal. For example, it's continuous time in seconds. So for each second I'm going to have, or even in milliseconds, I'm going to have one data point, while here I map into a much smaller space, which is the frequency space, and I'm going to have one frequency. For each point, it will be one frequency.